So this talk is about a work we did for ICML 2023 with Stéphane Ribaud, with a postdoc in my lab in Sorbonne.
He was a professor here at Fournier University in Milan, and invited me for the pre-mark.
Michael Eichenberg, who is at Flatiron, and Edouard Yellon, my supervisor at Sorbonne. And the idea is to work on a forward gradient, which is an alternative to backpropagation, and in particular through the lens of local learning. So the outline of this talk, first I'll just give a quick motivation, explaining what is forward gradient, what is motivating it, and how does it work. And then more generally present my method, so which is a general framework for forward gradient, in particular using gradients from local losses. Then we will present the main findings of our study, showing that we can reduce the gap with backpropagation. And finally, do a dynamics comparison to study how local and global gradients are aligned. Okay, so what's the idea behind forward gradient? The idea is to find an alternative to backpropagation. Backpropagation, as you know, is the ubiquitous method to compute stochastic gradient descent in a deep neural network with one-for-one and backward pass. Everyone knows about it. But although it's very efficient, there's still some drawbacks with backpropagation. One is that it's biologically implausible. What I mean by that is that there is, for instance, the weight transport problem. When you do a forward and the backward pass, you need to have the weight both for the forward and the backward pass, which and it's implausible to have a connection both in the forward and the backward sense that would have the same weight for both cases.
So you need weight is impossible because everyone is saying this like always very skeptical on this plane.
Because you generally between neurons you don't have two-way connections. You have one-way connections.
So it's going one way.
Yeah. So if we think that we have so for one time, if we think we have one connection which does the forward propagation and one connection that will some way retropropagate the gradient, this means that you have two different connections, so two different synapses, but both have the same wake information to compute. Yes, that's one of the reasons. I think there's also some more prosaic reasons, such as we never saw something as deep, I think.
Okay.
But, yeah, that's a motivation for a lot of alternatives to backpropagation. More practically, there's also other computation drawbacks to backpropagation. The first is that it's backward locked. What do I mean by backward locked? I mean that you must wait for subsequent layers to complete their backward passes before updating the layer you're computing. So you can say, of course, but there are other learning frameworks which only works with forward passes where you are not backward locked. This could be interesting to get a much faster computation. Finally, it's also computationally expensive. Even if it's very efficient, you still need to store the intermediate activations in your during backpropagation, during the forward pass. And of course, as you know, if you start scaling your network deeper, at one moment you will be stuck at your memory cost. And also, it seems a bit costly to do both one forward and backward pass. It would be nice to have a forward-only learning algorithm. Okay, so this is why it can be interesting to find some alternatives to backpropagation. Now let's get a bit more in detail about backpropagation. Another word, maybe not as catchy, is reverse mode automatic differentiation. This is what we call can call a backpropagation, and we can I will just use the slides from Nima Gravy, which we did a tutorial on atomic differentiation, because it's a really nice slide to explain what I want to show. If you have a function f, which is made by a few layers, for instance, just say that's a neural network, which takes an input size, a vector of size n, and as a scalar output, so just a loss. You see that you have your activation, your intermediate activations, A, B, C, and finally your output y. And this gives all the activation that you will compute in a forward pass. Now, how do we compute our gradient? If we do reverse mode automatic differentiation, so backpropagation, we will get exactly our gradient of our function. And we start from the output. So what do we do exactly? We do what is called a vector Jacobian product. What is a Jacobian here? It's a Jacobian of the function f. It's a scalar function, so actually the Jacobian is a gradient. And the vector has the size of the output of your Jacobian, so just a scalar. So it's a lot of talk just to say that we are multiplying one with our gradient, actually. But not that we are starting from the output. That's what's interesting. We are computing the product starting from our vector, and when we will do our chain rule, we will every time, when we do our matrix multiplication, we will collapse the computations to a single vector. And we do this every time for the next, the earlier layers, and at the end we get just our gradient. Okay, seems a lot of complicated explanations to explain backprop, but now it's interesting is that, of course, you guessed that if we talk about reverse mode automatic differentiation, there is a forward mode. So what is forward mode automatic differentiation? So that's the basis of forward gradient. The idea is rather than doing a vector Jacobian product, we do a Jacobian vector product. So rather than multiplying with our Jacobian, which I repeat is the gradient, a scalar at the output, we will multiply a tensor at the input. So this vector can be called a tangent or a perturbation, and this gives this scalar. So just a scalar product between the vector and the gradient. And you can just recognize that this is a directional derivative of your function f along the direction b. And okay, that's still less informative. So what's the interest in this is that you can do this only during the forward pass. Compared to the reverse mode autodiff, where you started from the output to compute the gradient, now we are starting to collapse computations from the input. So we start here with our direction v, and we will multiply starting from the first Jacobians. And then in the end, you obtain this scalar. Is everyone okay? Yeah?
Could you lower the other board? Is that possible? Lower the board or another screen on this side?
I think there is, but the pro I see.
You can move a bit if you want. It's better if I make this. So we didn't think about it.
No, there's only one screen.
It's not possible to move it from left to right either. Yes.
Oh, is it? Yeah.
On the right.
I don't think we can do.
No, I moved the screen there. I want to remove this.
I don't think.
Sorry.
Okay, so this is a forward mode automatic differentiation. So it's a way to compute a directional derivative of your gradient. So now, what is forward gradient? So there are several ideas with similar names. Now I think generally called forward gradient. The idea is just to gain an estimator of your gradient using this directional derivative. So yes.
Just forward gradient is something which is different from forward mode.
It's not really clear. Generally, when you say forward gradient, it's more about the estimate that you can, the estimate of the true gradient that you can gain with forward mode automatic differentiation. Automatic differentiation just gives you this part, the scalar product.
Yes, it gives you like the gradient.
Yeah, the directional derivative, yeah.
Yeah.
And when you say a forward gradient, generally you say this scalar product times the perturbation.
Because it's what you want at the end.
Yes, what we want, and in the end, is because we just add a scalar. Don't give a lot of information. We want, but we would like to have a gradient.
Like the full gradient, it's also like the scalar product with gradient FB.
Yep.
It's like the full gradient of the.
Yes.
Okay.
Yes.
Okay, and this is what you want to.
Yes, that is what. This is our estimate of the gradient.
I see. So
this is just actually just a projection of the gradient alongside the direction.
So I think for clarification, the thing is that in the backward mode, you are storing a lot of memory just for the backward pass.
Yeah.
Therefore, by being in forward mode, then you gain a lot of memory. And basically, you can estimate the gradient, but just by saying I'm doing like of the function value along one direction. It gives you like an estimate of, it's like a very rough estimate of the gradient. I'm pretty sure you're doing something smarter than this, but it's like one example of something you can do.
Well, I think this is what when you do finite difference, you get an estimation of the.
Yeah, it's an estimation. So yeah, what I'm saying is that it's a rough estimation, but
with forward mode to differentiation, you directly get this value. Yeah, the true directional derivative.
Yeah.
It's a direction. The point is the gradient might have n components. The directional derivative.
Yes, just a scalar.
A number in a direction.
Yeah. Yes.
So you might need a lot of those.
Yes. As for next slide, no, let's just stay optimistic for now. Even on this slide, everything will come crashing down. Yes. For now, yeah, let's say it's nice. We have an unbiased estimate of the gradient of our function. If you have any random perturbation with independent components, zero means and unit variance, we have an unbiased estimate. We can also say that rather than having a random estimate, we could just use n basis vector to get the exact value of our gradient. Yes.
So when you talk about estimate of the gradient, because the true gradient, there's no.
No, I don't have it. Because I am computing only forward mode automatic differentiation. So the only thing I get is this scalar product.
Yes, but at the end, you have like the true gradient what you want. No. If you're doing forward mode or backward mode, it's the same. Like you have a chain rule, the last product.
Yeah, but
you compute it in one way or the other way.
If you were computing entirely,
yes.
Okay, I guess what you mean. If we were just, it's usually a bit confusing here. When we talk about forward mode differentiation, we are not just starting from the input. We are always doing a Jacobian vector product. We are not just computing the Jacobian, which is enormous.
Usually like Jacobian vector product.
Yeah. And so with the Jacobian vector product, we just have, we do not have the gradient, which is all this. Since we already started.
Oh yeah, you have gradients times something.
Hindi po na tayo gusto parang.
Sorry?
I don't know where this comes from.
But I think the thing is like, okay, you do not have the gradient. You have the Jacobian, but you have the Jacobian vector product.
Yes.
Which is the gradient of the vector.
It's a directional derivative, it's not the gradient. I don't have at the end of my forward mode automatic translation, I have this scalar.
But f is going from which space to which space?
Yeah, it's not really clear.
It's a function of
in general, you could say that it's just a function of the parameters.
okay, there's like a function that goes from RP to R.
Yeah.
Okay. So what you're saying is that when you compute this Jacobian vector product,
Yes.
you never truly have gradient of F.
No.
But you have gradient of F of P.
Yes. Yes.
Okay. But okay, this is exact. It's not apples. When you do forward mode or back.
No, this is not random if you know the perturbation, if you know the tangent.
Usually you don't know this.
Well, no, well, in forward gradient, generally it's random. But you could also just compute it n times with V being all the basis of Rn.
Yes.
And you will get the gradient.
Yes. Okay.
Where I'm talking about an estimate is here when V is random.
Okay. But for forward gradient, we are computing this with V, the canonical basis, and you get.
You could also do forward gradient like this.
Yeah.
But for the basis, I'm just talking forward gradient. Like it's generally introduced and with a random direction. But we will look at over perturbation.
Okay.
Yes, so as I said, there's a random, you can have a random direction that gives you an unbiased estimate of your gradient. You could also just use n computations to refine the gradient, but then you are losing a lot of the advantage of the method. So we can get an inexpensive estimate of the gradient with a single forward pass. It's only update locked rather than backward locked, which means that you only need to do a forward pass. But I think you would have realized it's not really used in practice. And of course, you know the issue with this is that just a ridiculously high variance, since it's scaled at least linearly with the number of parameters of your input. You can, I think you can do the best variance using a one-measure distribution, but you're still stuck. Okay, if we can't really have a better perturbation, maybe we can have a better function to estimate. So there have been tries to, rather than estimating the entirety of your loss, just estimate a local loss. What's the point is that you use less parameters. So you're estimating a smaller gradient, and so the variance is lower. But at this point, you're just trying to estimate a worse gradient, so it doesn't really seem interesting. In this work, we do a general study for our gradients, where we are going to vary the gradients that we are trying to approximate, and of different perturbations for the direction of the forward mode OTD. Yes?
So just another question. Is this linked to what people call like feedback alignment?
Not really. Not too much. There's some
Connection.
There's some connection. It's another alternative backpropagation, but not too much. But yeah, if you're interested in this, you should check out feedback alignment. Okay. So what's our method? We are going first to introduce what is local learning. Local learning, it's another alternative to backpropagation. It can also be called layer-wise learning or greedy learning. And the idea is if you have your full network, you will divide your network into blocks or modules, and each block will learn separately following a local loss. So here you see you have a small auxiliary loss that will be used to propagate gradient through your first module. And your first module does not get any gradient from your second module. There is a stop gradient operation. So there's still a forward connection between modules, but you are only getting gradients from your local losses. Okay, why am I talking about this? Well, it's another alternative to backpropagation, which helps to compute an expansive gradient. It's an update unlocked algorithm. And the goal is also to approximate the end-to-end gradient. So this is starting to get a bit familiar. And the main idea in our work is we would like to find a perturbation that's already a good guess of the gradient direction. So just not have an estimate that is equal to 0 all the time. So why not just use another gradient, maybe? The idea would be to use a small auxiliary network with a local loss to provide an inexpensive gradient that will be used as the guess direction for the forward mode automatic differentiation. The drawback is now that we just have a bias estimate. We have no idea. Actually, there's no convergence guarantee on what we are computing. We are taking one direction and trying to estimate another. So that's the main idea behind using local losses. And the general framework that we will use here will be to divide a network into n modules. And each block, we will do a forward gradient estimate. And we will vary both the gradient guess and the gradient target. What is the gradient guess, gradient target? What we call a guess is the perturbation direction inside the forward gradient. And the gradient target will be the function of which we are trying to approximate the gradient. We'll see that there are several choices that can be made. And here is, for instance, what happens if you have the gradient target is just the full network, like before, and the gradient guess is come for the gradient of a local loss. So here we are at block G, and see that we have AG, a small auxiliary net with a local loss, that provide a gradient G tilde. So this will be what we call our guess. Now we are going to propagate, like before, the forward, in the forward our output of the module, but also our guess direction G tilde. And using a Jacobian vector product, we will obtain the scalar product between our guess direction and the gradient of our target, which here is the entire network. And with this estimate, we will use it to update our parameters. It'll be a bit more precise later on how we update.
Okay, question.
Yes.
So the AG
Yes.
sorry, is the module that estimates the gradient.
That's it's a local loss. It's like, for instance, just a small MLP with the concentropy loss. We train it and we receive a gradient from it. And since it's very small, it's easy to get a small gradient from it.
And the input is basically the output of the
Yes,
the
the output.
layer before.
Yes, it's if xg is the input of the module fg, at the output you have xg plus 1, which is used for this module and the auxiliary loss also.
And you propagate also the estimates after this. So you propagate the big G.
Yes, yes. This is, yeah, but not as a forward connection, but with a Jacobian vector product,
Okay.
as a tangent perturbation. Okay, that's a general framework on which we're going to work. Yes? How do we train what? Oh, it will be trained like normal. Like, yes, it has an input xg plus 1. It's, yeah, in our framework, it's just image classification task, like for the rest of the network. It's the same loss, actually. Yes. Yes. Well, you can get the gradient with regard to the input from this small loss, like you would guess for the rest of the network. It's just that here is much smaller. No, we do not. There is no explicit alignment between both. Since we are a bit stuck, we don't really have a lot of information to feed our auxiliary loss to align it better. And we'll see that it's a bit of a problem. Well, the idea is that AG is a scale down with another initialization, for instance, version of your real network. But yeah, there's no guarantee at all that we will get a similar. They are training on similar tasks, but there's no specific link between both of them. Yeah. Yes. Do you mean in local learning in general? You have all the right questions. In local learning, this is a big issue because I'll talk a bit about this later. In local learning, generally, you just use the same loss as you have at the end of your network. But you just logically, it seems a bit weird that you will train the first or second layer of your neural network directly to classify.
There's no projection head?
Yes, there is a small network that does a projection
At each level?
Yes. And the bigger the projection, the better it works. But still, the loss doesn't seem really, what's the word? Doesn't seem like the good loss to use at the early layers. And this is the problem in local learning in general, which has not really been solved. Some works, I tried in another work some variation on this, and there's also work that try to do reconstruction loss to try to keep features in the network informative. But still, it seems like a lot of tinkering, and we need to find a good way to find better losses. So this is a bit different. I didn't read too much about the forward algorithm. I think it's a sort of a contrastive algorithm, a bit Hebbian, but not really. It's not really related, but no. It's yeah, I would say it's closer to feedback alignment or for Hebbian learning, I guess. The idea is to have a very simple and much more biologically plausible learning protocol that you can do only in forward passes. But yeah, for local learning, we also have a similar op to have only with forward passes and train locally, but it's not exactly the same. Yes?
So maybe one last question, because I know in the paper you mentioned that local learning has been used also for log updates of the layers, right?
Yes.
How is it like really like you use it as a loss? You know,
Can you repeat the question?
like I know that you mentioned in the paper
Yes.
it's linked to like the greedy layer-wise training.
Yeah, it's another word for local learning.
Okay, so it just means it's
Yeah, if we wanted to, so we are going to also talk about local learning in the article. So if we were in this framework, it would be just using this guess direction here, just directly using it to update your module. But here we are trying to see if we can approximate the target gradient. Okay. So as I said, we can have different type of targets and guesses in our power gradient estimate. For our targets, it pretty much means that we're going to vary the depth of the target. We'll call global target just estimating the entire network, the rest of your network, just estimating by propagation. If we say a local target, it means estimating the local loss directly. So as what did René et al. In a previous paper. In this case, the idea is just to have a smaller variance, an easier approximation. But it's a less interesting target, as we discussed. But we also looked at an intermediary target, which is just to look at the local loss, not of this block, but of the block just above. And of course, you can do this for any k, any value of the local loss. For the guesses, they don't vary more in randomness. So generally for our gradient, you have a random direction, a random perturbation, which gives an unbiased estimate, but with very high variance. We have a local guess, which is using a local loss to get a gradient. And we have a sort of an intermediate, which we call LTK, which is maybe a bit abusive, which is a gradient from a random local loss. So it's exactly like the same thing. A local loss gives us a gradient, but we will reinitialize every time the local loss, so as to have some element of randomness, but also really see the impact of the architectural bias of the gradient. And that's the main type of targets and guesses that we will look at. Okay, I'm not going to spend too much time on this. Just know that there is a table if you want to look a bit more in detail on using, there's a trade-off, of course, in using deeper targets and less random guesses to using, it uses more compute and logs more the computation, of course. Okay, a bit more precisely, what exactly are we doing to update the parameters? At block FG, you can actually approximate gradient in two ways, from the activations or the weight. So we have this gradient, which is the one which we want to approximate, which is a gradient for one batch of the target on our the output of our module. So just the average for every input XEG. And we can directly approximate this gradient using a for gradient. This is the one pretty much that we presented until you have a gradient that is the size of the parameters, and you approximate it like this. But there's also another way to approximate our gradient. And it's just to remember that this gradient, you can just write it as the Jacobian of your module FG for your input XGI times the activation gradient of your target.
Thank you.
Thank you. And we can approximate our gradient directly on this activation gradient. And then, in this case, this is just a complicated way to say that we just backpropagate inside the block, starting with just the estimate at the top of the module. And note that for activations, we need to have a different estimate per sample, since this depends since you need to have a different Jacobian for each input. Yes?
So the second line is very clear, so basically like you decompose the gradient and you only estimate one part of the
Yes.
problem.
Yes.
But that's the first line, like what is
So we are directly approximating the average parameter gradient for the entire batch.
okay.
And in this case, you can just use an average for the entire batch.
Okay, you just use an average of the gradient
Yes.
of the batch, okay.
Yeah, so maybe you could just write 1G, maybe one approximation for one guess for the entire batch, maybe.
Okay, one guess on it, okay, yeah.
Yeah, no, maybe it's not very, I agree, it's not very clear. Maybe we shouldn't have waited like this. It's to stay consistent with the activation. Okay, so we have a framework, we have different type of target guesses. We know how to update the parameters. For the rest of the framework, we just have ResNet 18 divided either into 8 or 16 blocks. In the case of 16 blocks, we have no slip connections. So divided into 8 blocks for ResNet 18 means dividing by residual blocks. And when we divide by 16 blocks, we divide into even smaller blocks. We'll just use standard image classification datasets like CIFAR10, 100, ImageNet 42, ImageNet, and fashionist. Yes?
When you say just connection, independent part of the ResNet?
Well, when we want to divide in 16 blocks or ResNet, we are under the residual block size. So just to make it easier, we just remove the slip connection of the ResNet, and we have just checked that for ResNet 18, the skip connection does not do a lot.
Okay. All the skip connections are just between the blocks.
Well, all of them. So there's just 8 skip connections. No, for the ResNet, it's 16 blocks, it's not exactly. But
it has less.
But
It's fine.
but we checked.
It's okay.
For our standard for image classification dataset, it doesn't change anything.
Really?
Yeah. But we only did until ImageNet 42. But maybe for ImageNet it will start to get a bit. But just for ResNet 18 on CIFAR10, there's nothing.
I'm not an expert, but people are all saying that connections are very important to stabilize the optimizer.
Yeah, if you're starting to use really big data sets. Here we are just we are not at the large scale yet. We just stopped at
ImageNet is like 1 million.
yeah, but ImageNet 42, so it's still okay.
If the size of the image is big, then you need like this residual connection.
Yeah, but ImageNet 42 means that you're using 32.
What you're saying that you need this connection in the image.
Yes, but we could adapt it for. We could have added the skip connection. Just it seemed clear for here to just remove the skip connection and just divide it. Yes, I agree. It's not really just ResNet anymore in this case. For our local losses, we have 3 different types of CI networks. So once again, the CI network is a small projection that is done from your output until your local loss. So there's a CNN, an MLP, and just an average pool and a linear layer. And we always tweak the parameters so that we have auxiliary networks that are under 10% flops of your main block. So the goal is to have very small auxiliary network, just very inexpensive. And these are trained, like you said, with cross entropy, like the main network. And for the rest of the details, it's pretty much a standard training procedures for these datasets. Okay, what did we find? Well, we found that using local guesses grants the best estimate of the global target by far. As you can see here, we have in red your training loss for backpropagation, and in blue for using local guesses for gradient. And as you can see, when you do random guesses in purple, you do not converge at all. You slightly improve using NTK guesses, but you do not converge globally in general, and it doesn't seem really interesting. Okay, more in detail. Well, what does that mean in numbers? Well, we can reduce the gap with backpropagation. In backpropagation, for CFAR10 gives pretty much a 95% accuracy. And using local guesses, we can reach up to 92% accuracy. Yes?
So I just have a question on before.
Yes.
So in terms of epoch, but should be much faster per epoch. Your method. Si tu peux pas compléter full background.
Yes, if this was really well implemented, it would be much faster. For a very good implementation, it would be great.
But you can manage to have a good.
No. When this was like 1 year and a half ago that we did this paper. This was at the start of FunkTorch, also called torch.funk. So we did not use it at this time, but now, this is a lot of simulation of for a minute. We are not really competing directly with torch.funk, the vector Jacobian product.
Yeah.
But if we did, we
would be like very interesting to see that okay, you're like 10 times faster and very similar.
Yes, I think that would be a point to sell it, but yeah, in the end, I don't want to be too pessimist, but I feel like we are not there yet for events.
Even like for large language models, for instance.
Okay, this is where it starts to become interesting because yeah, just after our paper, there's also an article called Meso. I think it's called Meso. We did zero order optimization for LLMs.
Okay.
So this just doing you said any difference.
Final difference.
It was used to fine-tune LLMs.
Okay, fine, that's fine.
And in this case, they said, it works pretty well. In a ratio of time compute, it start becoming interesting. But we were just focused on can we just train it?
Yeah, it could be like, and maybe can you comment like on the implementation challenges?
I mean, honestly, now I think it will be relatively easy to implement. I know much more about implementing VGPs and GPPs, and I think you can be pretty fast.
Maybe JAX would be easier because you can easily.
Yes, you could do it easily with JAX. But torch.funk is
pretty
much the JAX equivalent. They want to have a very functional way to implement gradient, Jacobian vector products, Jacobian star. That still doesn't mean that it would be a much. I mean, we are still competing against the very optimized.
Sure, but could be.
Yeah, we could be. But yeah, since what we're going to find is that either random guesses are impossible to converge.
Yeah.
Or in our case, we are able to converge but not reach exactly backpropagation. Even if we get much faster, even we gave more time, I don't think we will really.
I don't know, because I mean for large language model, since you cannot train it cluster, so you could have something.
I mean, yeah, maybe a possible way to do it would be to have our method to do the start of training, to really start training with for model. And then in the end, you can do the unbiased estimate or the zero order difference method to really finish your.
Excuse me. I have a question about this. It's like local guesses means a local optimal.
Okay, we can go before. So I don't know if you're too familiar with forward gradient. The idea is that in a forward mode differentiation, you can compute the scalar product of one perturbation vector G and the gradient of a function f with only one forward pass. So you don't get exactly the gradient, but you only do it in the forward pass. And when you multiply it to the direction G, this gives you an estimate, which is the forward gradient. Here, what we want to see, rather than doing a random direction G, is to use a biased estimate, but with some chance which is a bit aligned with the gradient vector gradient of f. And G here will be the gradient coming from this local loss, AG. And this is when we call local guess, this is what we are talking about. Gradient coming from a small auxiliary local loss. That's okay? Yes.
Yeah, so I have a question. So with the method, the big issue was it's like 40 to 100 times slower. So you need almost 100.
Slow and
Yeah.
Converge because it's made bad.
No, in terms of time.
Use 40 to 100
In terms of time, like computing the estimate of the line is faster.
Yeah, it's faster, but it's still
It's time estimate.
To train the network, it takes.
Oh, yeah.
Fully train your network.
Not enough to compensate for the fact.
Okay.
So it's not 100 times faster. So
Okay.
Okay, and when I talked with them, I said, well, why don't you just use like forward gradient for automatic translation, because you will not need to use another estimation with zero order. Maybe it will be faster to do this. But they say that their big selling point was memory, and I think that's what the justification.
the memory should still be there.
Yeah, I don't really understand what she meant, but.
But in your case, the graph was the same number of steps.
Yeah, it's just by epoch. Yeah.
So that's the nice thing.
Yes, that's a nice thing.
Okay, and was it Adam or SGD?
SGD with momentum, I think.
And is there difference Adam versus SGD?
I don't think it changed much. I think we tried it, but we kept SGD here, but I think we tried Adam and we were the same thing. Well, which is that it converged, but there's still a gap. There's this annoying gap that we get, which is pretty much due to local learning. We'll see. So yeah, for accuracy, we have, so you can see that we can reach pretty close to backpropagation, but we're still not there yet. And when we get to more complex data sets, it becomes much harder. What can we get from this table? You can see that there are better performance for weight perturbation than activation perturbation. We are still not very clear why. Maybe by having the same, there's maybe a variance reduction in the batch, the fact that we have one estimate for the batch. Maybe it's more because activation perturbation is not smooth with regard to the input, so there's just 1 degree more of perturbation possible. We're not really clear yet why, but this counters what was said in the previous work, which said to focus on activation perturbation. But so I would say it depends. Maybe try both if you're doing a check. In your case, it depends much on the model, on the size of the block, etc. Maybe just look at it. And we have, once again, sometimes, not always, more performance, better performance with the CNN than the MLP auxiliary net, probably due to the architectural bias of this model. There's also better performance for bigger blocks, so here for 8 blocks compared to 16 blocks. Maybe some of this can be attributed to the fact that as we have bigger blocks, we can have bigger auxiliary nets, since our limitation was to be under 10% flops. Since it's something that you can also see in local learning, when you have deeper or bigger auxiliary net, you have better accuracy. Yeah.
So maybe local load.
Yes. Yes, it's average pooling, like 2 times 2 average pooling, flatten and linear layer directly. To be sorry? Yes. Yes, but when I say the linear auxiliary network is average pool plus linear. I just gloss over. Yes. Yes. It's pretty much the same effect than in local learning, actually. when you get bigger and deeper networks, well, you will see that the main problem of the alignment of the gradient is in the early layers. So it's the same problem that for local learning. The task which we are training our early local layers is not at all the same task that is trained for the early layers in backpropagation. The early layers of your CNN are not trying to classify as quickly as possible your data. But so by giving a bigger and deeper auxiliary net, you are mitigating this effect by introducing depth in your auxiliary net. Yes. Yes. Since in our case, we really wanted to really limit ourselves to very basic ID. Under 10% was very, very small. For the smaller layers, it was like 16 channels for CNN, 3 layers, something like that. So very, very small. But yeah, you could get much better results if you increase the accuracy. But you start to lose the interest of the method, since the goal is to have really small. No, this is for a gradient. This is the results are for a gradient approximating the global target with either local, NTK, or random guesses. Maybe I wasn't clear. Sorry about that. Is that clear? Oh, this is just a point. This is just a comparison. No. No, I was talking for later in the talk. I talk more about local learning later. What can we also see? We see that even the NTK guesses improve on the random. So just forcing to, even if they are completely random, having a gradient, even from a random network, still improve on a random. And you can also see that despite some claims, doing Gaussian or Radmacher distribution doesn't change anything. You still have the same issue. Okay, we can have some more insight if we look at the training of different frameworks, and we look at convergence, the train loss of the local layers, the local loss. So this is early in the network, and this is deeper in the network. The goal is just to see at a different point of the network how well you have the local losses have converged. So the first thing, just to get it out of the way, when using random guesses, you see that the local training loss increase. So just to show that it doesn't converge at all. When you do backpropagation, what do you find is that you have a very slow decline in local train loss compared to local learning. So this is what we talked about. When you do local learning, you have a very quick convergence of the local losses in the early layers. You see that you reach pretty much 0 at block 2. And this is due to the fact that we are doing some greedy training. In early layers, we are training our blocks to very quickly minimize their local losses without any consideration for the further blocks. So of course, we are training to minimize this loss, and this leads to poor representations for the later blocks. But when we are doing forward gradient with local guesses and global target, so our main framework here, you see that we have a somewhat similar dynamics than for backpropagation, with a reduction of the effect of greedy training. Even if we are using this greedy gradient as our basis, we do not have this greedy effect of small train loss for the early blocks. Okay, pretty much just talking about the global target. What about the other target? Well, sadly, it's not really interesting. There are better results with random guesses for the global target than with the local target, which means that it's better to approximate with forward gradient the end-to-end training loss rather than the local losses. Compared to other claims on forward gradient, it doesn't seem really interesting. even when trying to do a bit of an intermediate between both, using an intermediate target, like we said before, local losses a bit above. So it's a closer objective to approximate than the global target, but still, it doesn't give a good representation for the entire network. So a lot of talk, just to say, just try to approximate the global target. It doesn't really, doesn't seem like a really useful shortcut to try to approximate some kind of local target. So there are more experiments in the paper. You can see the consistency across data sets. So one of experiments that is also interesting is we tried a wide ResNet. So just wide ResNet is you have a wide width factor which increases the number of features if you're in your ResNet. And you can see that as the model widens, of course the end-to-end accuracy improves, but also the accuracy for your local guesses. So this is probably due to the fact that we have bigger local losses, but this also shows that this is in comparison to random guesses. When you check random guesses, you see that their accuracy actually decreases as you have a bigger network. This is, of course, logical with what we talked about. As the variance increases, your estimates are worse and worse, and you have a worse result. So this seems to indicate that you can start to see the interest of our method, mainly for bigger networks. Maybe. Okay, so we have made a better idea of how our model, our framework works. Now let's look at dynamic comparison. We would like, so we have seen that our algorithm can converge with local guesses, but we are still not really clear how good is our estimate. And since there are no particular reason for our local and global dynamics to really stay aligned, how do they stay a bit similar during training? So one easy way to do this is just to measure the gradient alignment, which is just the mean cosine similarity between your gradient from the local losses, so your local guesses, and the gradient from your network, so the global target. If the cosine similarity is equal to 1, where you have perfectly aligned gradients, and if the similarity is 0, you have they are completely independent from one another. If it's equal to -1, if you're aligned in the other way. But I don't know how you would have done that. Okay, what do we find? There's a lot of stuff to talk about in this picture. This is the cosine similarity between local and global gradients in the case of 8 blocks on CIFAR10, and for the 3 different auxiliary networks. So as you can see, the first thing to notice is that we are constantly positive. We are aligned, despite not giving any indication between the local and the global networks. We still say somewhat aligned. So we show that this idea is not too stupid. There's a good idea of this seems like a good idea to use the prior to use a gradient. You can see that not the y-axis, you have a much higher alignment for the later blocks compared to the earlier blocks. For the first blocks, we are around 0.1 or 0.2, and here we are at around 0.6 or 0.8 even. Okay, why do we have this? This is pretty much what we talked about earlier with local learning. When you are at the end of your network, you just have like a few layers remaining. And so when you have a small auxiliary network, these are pretty much the same task. They are not the same network, not exactly initialized the same way, but you have very similar tasks. Your goal, you have the same kind of representation, and your goal is the same, just to finish separating, linearly separate your features. But when you are at the start of your network, that's where the problem appears, is that you do not have at all the same task. And that's pretty much what you can see in local learning also. You have the same issue. The tasks are for all layers, not the same one at all. Because you have a very deep network compared to a very small, shallow network. Yes? Well, first here, this is our activation gradient, and here this is our weight gradient. So they are not very Similarly, they're not exactly similar, the same size. Honestly, I think they're pretty much the same since it's after the first projection layers of your ResNet. So there's a difference since we are, as you get deeper in your ResNet, you downsample your image and you get more features. So the ratio is not exactly the same, but you stay pretty consistent. So the big drop in quasi similarity cannot really be attributed to a difference in dimensions. But yes, it's not exactly comparable. So there's also, once again, it's not really clear, some kind of better alignment for the functional neural network, in particular for the last layers. You can see that the architectural bias really appears in this case. You can also see that the alignment is much better for the weight perturbation. So this seems logical since we found that there are better performance for weight perturbation. Once again, it's not extremely clear why weight perturbation are much better. And finally, you can also see that you can generally have some kind of decrease of alignment during your training. You can see the three, this is a simple step LR schedule, so 3 learning rate steps, and you can see them in the alignment also. This seems to indicate that as your local and your global losses both reach some local minima, they stay farther and farther away from each other. But yeah, we would like them to stay close together. But since there's no really a way to keep them close together, we have to stay with this. Okay, so we have a positive alignment, which is pretty good, but it's still not quite poor. Can we do a bit better? There's a simple way to check that. We wanted to check if we add the entire local gradient subspace, would it be even enough to project our target gradient? What do I mean by that is that if I had the last million gradient that I could have from my local losses, the entire subspace, would it be possible with my forward gradient, which is a projection on this subspace, to reconstruct my target gradient? Or is this just, or the subspace not aligned enough or too small for the local subspace? Well, we can have a small proxy of that by just having a batch of target gradient projected on the span, the linear span, of a batch of local guesses. So we can represent it like this. For instance, if you have 2 different guess directions, you have a better estimate, better projection of your target. But if you just stay on this plane, for instance, you see that it will still not be good enough. Yes.
Just to be sure, so here you're basically trying to test the limit of the method. So
yes.
You're not
yes.
actually using something that will be used in practice.
No,
because you're using the
yeah. This one is really the limits of what could be.
What could be the best possible method among the class of methods?
You could do it. We talked about it. You could, for instance, get a batch of local guess, do some kind of PCA, and project on the K first principal component for your gradient. But then you start to have a trade-off between the number of components you do, and so maybe it's not really interesting. But yeah, it's a trade-off, and it's more to test our hypothesis than to say that it's really doable. But yeah, if you do this, of course, you improve accuracy because you improve your projection. But it means that you are doing more computation, and you can get an increase in accuracy. But still, it's more consistent. But it's still not good enough. So this seems to indicate that the local gradient subspace is too restrictive, and maybe not aligned enough to project entirely your target gradient. Well, that seems a bit obvious now. Of course, you do not force them to stay together, so this is logical. So we need to find some kind of better alignment. The final name in the coffin is that, sadly, local learning is pretty consistent with using forward gradient with local guesses. So you could just, rather than doing this complicated Jacobian vector product, you could just use directly the gradient from local learning and get pretty similar results. You can sometimes get better results with our gradients. It depends really on the cases of the auxiliary size, etc. But our conclusion is that it's not really that interesting to do for now. For now, local learning is still provides similar results for never better unlocking.
So you're saying that instead of using the gradient of the local learning as a perturbation and then do the scalar product, it's just better to use directly the gradient from the local learning stuff.
Yeah, I mean, for the amount of computation and complexity that you will add for very similar results, if you want to have a very like blockwise learning, for now it's still better to use local learning.
So sad.
Yeah, that's a very sad conclusion, but we still made it work. And I think the reason for that is the same one as local learning. Is you have a misalignment in the early layers, and you do not have any feedback for your local losses. So you need to improve the equivalent alignment to improve the estimate. So the conclusion of what we showed is that forward gradient still does not match backpropagation, sadly, but you can very, very heavily reduce the gap if you start using other than not random perturbations, but start using guesses from local losses gradients. This helps have a consistent alignment with your end-to-end gradient, and so this helps have a consistent training compared to the almost null gradient that you get with random perturbations. But still, it's still a bit too early, it seems like, to really justify the use of forward gradient for now, since local learning provides a very similar accuracy. And so future works should find a way to improve the alignment. So we have discussed a bit some of them. Some kind of, maybe allow some more exploration, some more randomness in the distribution, since after some time we're a bit stuck in this local random subspace. Using different local losses, but this is the same kind of discussion that you will have in local learning, and find a way to modify the local losses during training. I started a bit doing this, but for now it was still not good enough. And it's hard to find a way to change to impact your local losses in an inexpensive way. Since the goal is still to have computation, to have a very efficient and framework where you do not have a lot of feedback from the rest of your network. So it makes affecting the local losses very difficult. There are also a lot more tables in the article if you want more of them. Don't hesitate to talk to me if you are interested in this subject. Thank you.
So, is there any question for me? I have one actually. So the way you compute actually the estimate gradient is by like plugging an additional small neural network with others which is similar to the original network.
Yes.
Correct. But actually it's not what you really want to do. So what you would like is to plug a network that tries to be as close as possible to the true regions.
Yes. Exactly.
And isn't it possible to do that instead? For instance, once in a while, like one time over one to compute the true region, and then you adjust the weights of the auxiliary network. Or you use, like, for instance, the previous estimates as, like, you do a fake backpropagation by using the other estimates of the region, and then you plug in and you try to compute what would be the true region, and then you adjust the weights of the auxiliary network that way.
I've tried doing this sort of thing, mainly just in the case of local learning, trying to find a way to do some backpropagation every like 10 steps, something like that, just to modify the local loss.
But not even modify the local loss. What you want is like in a network, input is the forward, the output of the layer, and the output is an estimation of the region.
So this is this can be called actually, but this is actually the article which I'm talking about a lot of Jaderberg. We talk about the different locking of your network. He introduced this in an article called Decoupled Neural Interface. And the goal is to do some kind of local learning by having a network that directly outputs gradients like this. But it works less well than doing AOS. I think just because outputting a gradient is not really easy for a network to do.
I mean, it's like, again, estimating a function somehow, which a neural network would do.
Yes, but
It's like basically compressing the rest of the neural network into a smaller one that tries to have a similar behavior for complete regions. I don't know. I mean,
I'm not exactly
if it
sure why.
had been done
It works, in the case of local learning, it works way less to
Okay.
have a network that outputs exactly the gradient, rather than having a local loss from which you get the gradient. I'm not exactly sure why. Maybe just because of the smoothness of your function with regard to the input, it's maybe complicated as a function to get. So I've been looking more into finding a way to change the local loss to get a gradient that is more aligned. This, once again, it's a bit tricky. But this is clearly, I think, a promising direction.
Okay. Because you can also try to adjust the local loss such that the output of the local loss is similar to the output of the true neural network. Like that could be something that could adjust the auxiliary network and estimate the gradient.
Well, I think you still have a kind of similar effect, greedy effect, like in local learning. If you just say have the same kind of output as the end of your network, you will still try to just classify too quickly.
Yeah, I see. Yeah, okay.
So I think maybe a more possibly interesting way is to find some way to regularize the local loss.
Okay, nice.
How do you compute a local loss, raising some layers and consider the raise as a local loss?
Yeah, maybe I want to
Sorry.
think about that. Is that in the case of the for, and we are doing for a gradient, the gradient that we are receiving here is there's a stop gradient operation. We are not using directly this guess gradient to optimize anything. And but you were asking how do we update this local loss?
Yes, to compute it from the network.
Well, between each modules, you have your output of your module x g+1, which can be used to either propagate for the rest of the network, or you can also use as the input also of your local loss. And you could train your local loss like normally.
Okay, one last question. I know that this feedback alignment, like Backpropagation method, they can work a bit if you don't have like reproduction, this kind of stuff, but they break as soon as you add this type of layer. So I was wondering if inside.
Not too much. I just knew that they don't work well in a real network, but I didn't know that that was a justification.
Because like you see, you're playing with feet, well, but not I was wondering if you have the same type of behavior with stuff like that.
We didn't observe this, but maybe I know, Leslie. I feel like this is just a justification to say that it works in smaller networks, but it needs to.
Okay.
Since there's not a lot of big MLPs. I don't know.
Here again.